Welcome to this explainer. Okay, today we are unpacking a technological collision that honestly sounds like pure science fiction, but it's actually happening in labs right now. We're talking about two massive, world-altering forces accelerating directly toward each other, totally ready to redefine the very limits of human discovery. Picture this for a second. Somewhere in a laboratory right now, the temperature has been cooled to nearly absolute zero. We're talking literally colder than the empty vacuum of deep space itself. And that's just to keep a single machine running. In that chilling, dead silence, this machine is trying to solve a problem that would take a standard computer longer than the age of the universe to crack. This physical machine exists today, built atom by atom, and it's about to collide head-on with another massive revolution.
So, for decades, we've had these two entirely separate technological rivers quietly carving their way through history on parallel tracks. Each of these rivers has completely reshaped our world independently of the other. But right now, they are merging. The convergence of these two distinct streams of innovation is set to unlock an entirely new era of discovery. Let's break down exactly what these two rivers are. The first river is one we're all incredibly familiar with by now: artificial intelligence. You already know the drill here. These are systems trained on vast, endless oceans of data to recognize hidden patterns and improve through experience. It's a discipline built entirely around navigating a level of complexity that human brains just simply cannot process alone. Then we've got the second river: quantum computing. Now, these are definitely not just faster versions of the laptop sitting on your desk right now. These machines exploit the bizarre, almost dreamlike rules of subatomic physics, where particles can literally exist in multiple states at once. It completely defies our everyday logic, but it happens to be the fundamental reality of how the universe actually works at a microscopic level. So you might be wondering, why pair algorithms that learn with machines operating on these weird subatomic rules? Well, because humanity's absolutely hardest problems have basically hit a brick wall. We've reached the limits of traditional problem solving. To make that next giant leap forward, we have to untangle unimaginable complexity. Let's look at the real-world stakes for a second. We are talking about designing life-saving drugs, literally molecule by molecule. We're talking about modeling chaotic global climate systems to actually prevent disasters, breaking or building entirely new, totally unhackable encryption. These are not just fun theoretical puzzles. They are urgent, pressing challenges that will absolutely define the future of humanity. Think about it like this. Traditional computers, no matter how ridiculously fast they are, process information one single step at a time. It's like walking a linear path through a massive maze. Quantum computers, they don't walk the maze. By exploring many possibilities simultaneously, they experience every single path of the maze at the exact same moment. It is a massive, game-changing leap forward in how we process reality. But hey, here's the catch. Exploring every single path at once, that creates an absolute ocean of data. I mean, pure chaos. And that is exactly where AI steps in. While quantum maps out those unimaginable possibilities, AI acts as the ultimate navigator, rapidly sifting through that massive output to find the exact perfect pattern hidden in all that quantum noise. Together, they form a remarkably complete system. Now, to really grasp the magnitude of this whole shebang, we kind of have to look backward. This convergence wasn't just cooked up recently in some slick Silicon Valley boardroom. It actually started with a profound philosophical realization. Our traditional computers are essentially speaking the completely wrong language if they actually want to understand the natural world. It goes all the way back to the early 1980s with the legendary theoretical physicist Richard Feynman. He proposed this deceptively simple notion on a chalkboard. For decades, it was just math and abstract academic papers. But today, that exact notion is actual physical hardware sitting in those deeply cooled labs we talked about earlier. Feynman pointed out something absolutely fundamental. He said, nature itself is quantum. So if you want to truly simulate nature, you need a computer that thinks the way nature does. That's the core philosophy right there. We aren't just building a faster calculator, we're building a mirror to reality itself. But, all right, here is the massive paradox of our story. Despite all of this incredible, world-changing potential, current quantum computers are incredibly fragile. Because they rely on those subatomic particles, a tiny change in temperature or even slight ambient noise can cause them to completely fail. It's actually kind of ironic. The most potentially powerful machines on Earth can be derailed by, well, someone sneezing in the next room. Right now, they are highly delicate and still largely experimental. Which brings us to a real high-stakes mystery. If this tech is really so fragile, why is there an absolute all-out sprint happening right now? The world's most powerful, well-resourced tech companies are aggressively racing to combine this delicate hardware with advanced AI. They are pouring billions of dollars into making this convergence happen right now, immediately. So I'm going to leave you with this final thought. If the smartest, most resourceful tech giants in the world are risking billions to force these two rivers to collide right now, despite the immense challenges, what do they see coming that the rest of us don't yet?
Welcome back to The Explainer. Today, we're digging into a single year that completely changed computing history, 2019. You know, it wasn't about some flashy new smartphone release or a slightly faster laptop. No, this was the year a massive fundamental barrier in science was literally broken. Think about it. Why did a quick 200-second calculation in 2019 totally rewrite the future of computing? It sounds like straight-up science fiction, right? I mean, how can a calculation that takes just over 3 minutes change the entire trajectory of human technology? Well, to really grasp this historical shift and understand the sheer magnitude of what happened in that tiny window of time, we first have to completely toss out how we normally think about computers. Okay, let's dive into this. We all know the deal with classical bits, right? Your standard laptop runs on strict ones and zeros. But 2019 proved we could reliably manipulate what are called quantum qubits. And here's the kicker. Qubits don't have to choose between a 1 or a 0. They can exist in a state of superposition, meaning they hold both values at the exact same time. This isn't just a tiny speed upgrade, it's a whole new paradigm. We're talking about a fundamentally different way of processing possibility itself. So, what does this actually mean? Because of superposition, a quantum system can evaluate vast amounts of possibilities simultaneously. Think of it like a maze. A classical computer tries to solve the maze by hitting every single dead end, one by one, until it finds the exit. But a quantum system? It essentially walks down every single path, all at once. And okay, it gets even weirder, which brings us to the next big concept, entanglement. This is the strange, mind-bending phenomenon where a change to one qubit instantly influences another, totally regardless of the physical distance between them. Imagine linking two of these qubits, moving them miles apart, and finding that whatever you do to the first one immediately and perfectly happens to the second. It literally breaks our everyday intuitive understanding of how the physical world is supposed to operate. Honestly, this concept is so bizarre that even Albert Einstein was thrown off by it. He famously called entanglement spooky action at a distance. And you know, when the guy who completely revolutionized physics looks at the mechanics running your computer and calls it spooky, you know for sure you're dealing with a wild new frontier. Now, for a long time, all of this stuff, superposition, entanglement, qubits, it all mostly just lived on chalkboards and in dense research papers. It was purely theoretical physics. But that brings us right back to our main focus today. In 2019, that theoretical physics became a tangible, working reality. The scientific world was hit with this bombshell announcement that proved this crazy technology wasn't just hypothetical anymore. 200. That is the number that changed everything. In 2019, Google proudly announced that its Sycamore processor had successfully knocked out an incredibly complex calculation in a staggering 200 seconds. And this brilliantly illustrates the sheer magnitude of what they actually pulled off. Google's Sycamore wrapped up the math in just over 3 minutes. For the world's fastest conventional supercomputer, researchers estimated that exact same calculation would take thousands of years. Let that sink in. We're not talking about a slight bump in processing speed here. We are leapfrogging millennia of classical computing time in an absolute instant. Now, full disclosure, this claim sparked a pretty fierce debate. Some experts pushed back hard, arguing that actually, classical machines could eventually catch up and perform that same calculation much faster than expected. But honestly, regardless of who ends up winning that specific academic debate, the main takeaway is absolutely crucial. The fundamental boundaries of computing are being redrawn in real time. Let's move to and see how this builds into another massive technological shift happening right at the same time. Artificial intelligence has already been quietly transforming fields across our entire world. From medicine to finance, AI systems are actively detecting cancers in complex medical scans, predicting incredibly intricate protein structures, and generating human-like language with just astonishing accuracy. Classical AI is an absolute powerhouse. But that brings up a really important question for the future. What happens when problems become too complex? Because despite all of its incredible current achievements, classical AI does actually have a ceiling. Even the absolute most advanced neural networks, running on top-tier classical supercomputers, eventually hit a processing limit. And here is exactly where AI hits a wall. When problems become too complex, too tangled with a practically infinite number of variables, classical AI really struggles. We're talking about massive, real-world logistical nightmares, like optimizing dynamic global shipping routes, or discovering entirely new, complex materials from scratch, or, maybe most importantly, modeling molecular interactions right down at the quantum level. The calculations just get too vast and intertwined for ones and zeros to handle efficiently. Now, what's really interesting about this slide is that this is exactly where these two separate technological worlds collide. Quantum computers natively process the exact kind of layered, probabilistic information that perfectly mirrors how neural networks actually make decisions. I mean, they are practically made for each other. Quantum mechanics effortlessly handles the tangled variables that totally trip up classical AI. It creates this beautiful, symbiotic partnership where each side compensates for the other's weaknesses. In step 1, quantum systems process massive probabilities to help train AI models vastly faster than traditional computers ever could. But because qubits are super fragile, like they can be messed up by simple temperature changes, step 2 kicks in. AI algorithms step right back in to correct the errors that plague those fragile qubits. One technology literally stabilizes the other. And just to ground all these abstract concepts in reality for a second, this isn't merely a thought experiment for the distant future. Researchers are actively exploring this quantum machine learning right now. This technique is already being tested by major tech companies like IBM and Google. The convergence of artificial intelligence and quantum computing started becoming a practical, testable reality directly following that 2019 breakthrough. So the crucial point is this. When you combine a machine that processes every possibility at once with an artificial intelligence that learns and corrects errors at unprecedented speeds, what emerges next changes absolutely everything. If 2019 proved the quantum hardware could actually work, and today proves that AI software can integrate with it, it leaves us with one incredibly exciting and honestly, maybe slightly intimidating question to walk away with today. What does solvable even mean now? Thanks for watching this breakdown on The Explainer, and keep questioning the possibilities.
This is the frontier. But the fragility of the qubit, exposed here, is the greatest challenge.
Welcome back to The Explainer. Today we're diving into something that is honestly both awe-inspiring and, well, a little bit terrifying. We're looking at the absolute edge of human innovation. What happens when artificial intelligence merges with quantum computing? We're going to break down the massive promise of this tech, the perilous physical hurdles, and a very real, very urgent threat to global encryption. So, let's get into it. So, what exactly happens when machines start to calculate like the universe itself? We really need to establish right out of the gate here that we aren't just talking about building a faster computer. No. We are looking at a fundamental, mind-bending shift in how calculation actually works from the ground up. Section 1. The quantum promise, solving the impossible. Okay, let's dive into this. Before we get to the scary stuff, the massive risks, we absolutely have to look at the utopian, highly optimistic possibilities here. Because, this fusion isn't just theory anymore. It's happening right now. In the pharmaceutical world, researchers are using quantum-assisted simulations to model molecules. Instead of years of physical trial and error, they're simulating molecular interactions at the subatomic level. We're talking about saving billions of dollars and potentially finding cures in a fraction of the time. Over in finance, institutions are already testing quantum algorithms to untangle incredibly complex investment portfolios, stuff classical computers just choke on. And climate scientists? They are watching this space so closely. They're hoping these models might one day simulate our atmospheric systems with total precision. Imagine having the exact foresight we need to tackle climate change. It's a real game changer. Section 2. The fragility of qubits. A delicate balance. But okay, let's slow down for a second. The challenges here are very real, and they're definitely not small. Actually, building these machines is one of the most massive physical engineering hurdles of our entire century. It mostly comes down to this thing called decoherence. Basically, decoherence is a phenomenon where a stray vibration, or literally just a fraction of a degree shift in temperature, completely destroys a quantum calculation. Right now, these quantum computers are notoriously unstable. To keep their quantum bits, or qubits, functioning, they have to be isolated in environments that are actually colder than deep space. I mean, if someone slams a door down the hall, or if there's the tiniest thermal blip, bam, the quantum state collapses. The calculation is completely ruined. So yeah, these supposedly all-powerful machines are incredibly delicate, which makes it super difficult to build systems reliable enough to outperform our regular supercomputers. Section 3. The threat to encryption, shattering global security. And that brings us to the most serious part of our explainer today. We're shifting gears from physical fragility to a looming existential cybersecurity threat that literally has the entire tech world on edge. Just look at the stark contrast between where we are now and where we're headed. On one side, we have classical encryption. This is the invisible shield protecting, everything. Your personal data, private communications, global banking, power grids, the whole shebang. But on the other side, the quantum threat. There are mounting, very real concerns that a sufficiently powerful quantum computer could completely shatter that encryption. We are talking about malicious actors being able to unlock practically any digital vault on the planet. The stakes are just immense. And it's forcing governments and tech giants into this panicked, urgent race to build new quantum-resistant defenses way before the hardware even fully matures. Now, you might be wondering why. Why exactly do quantum computers have the sheer power to break the encryption that keeps our modern world safe? To get this, we kind of have to look at how encryption works right now. Classical computers secure our data using these incredibly complex math puzzles, mainly by multiplying massive prime numbers together. For a regular computer to crack that puzzle, it has to guess the factors sequentially. It tries one combination, then the next, then the next. To guess those numbers one by one, our best classical supercomputers would literally take millions of years. But remember, scientists aren't just building faster sequential machines here. Quantum computation mirrors the strange logic of the universe. It calculates the way reality itself operates at a fundamental level. Because they use principles like superposition, quantum computers don't have to guess one by one. It's like a giant maze. A classical computer walks through, hitting dead ends, backing up, and trying again. A quantum machine, it floods the entire maze all at once to find the exit instantly. It processes vast multitudes of possibilities simultaneously. So that prime factorization problem that would take a regular supercomputer a million years, a mature quantum computer could theoretically solve it in hours, maybe even minutes. That is exactly why they are such a massive threat to our current encryption.
Section 4. History's lesson, from fragile to indispensable.
And this brilliantly illustrates why we have to take this seriously, even if the machines are super fragile today. Because this seemingly impossible, unstable tech, it's actually following a very familiar path. Let's look back at the evolution of computing to put this into perspective. Think about the past era. The very first electronic computers literally filled entire rooms. they sucked up massive amounts of electricity, and honestly, they barely outperformed a person using an abacus. They were highly experimental, super delicate, and they broke down constantly. Back then, nobody could have predicted our modern era, where those room-sized behemoths shrank down to fit right inside your pocket, connecting billions of people instantly. The sheer absurdity of that leap is just wild, and that's our lesson for the future era. Every single transformative technology looks impossibly fragile right before it becomes absolutely indispensable. We definitely can't let the current instability of qubits lull us into a false sense of security.
Section 5. A new kind of thinking, blurring simulation and reality.
So, let's bring this all together and see how this builds to a monumental shift in human capability. Because what makes this specific moment in history so profoundly different isn't just the quantum hardware. It's the pairing. We are witnessing something totally unprecedented. Intelligence that learns, artificial intelligence, is meeting a form of computation that mirrors reality. Just think about the gravity of that for a second. On one hand, you've got AI models that can rapidly adapt, recognize intricate patterns, and teach themselves entirely new paradigms. And on the other hand, we're handing those intelligent systems a computational engine that calculates using the actual physics of the universe. We're standing at the edge of a radically new kind of thinking. Whether this partnership fulfills its promise in 10 years or if it takes generations of engineering to figure out, one thing is for sure, the boundary between a computer simulation and actual reality is getting thinner with every single experiment we run. Which brings us to our final provocative thought. The debate isn't really about whether these two revolutions will merge anymore. It's already happening in labs all over the world. The real question you should take away from this explainer is, what will we discover? And what will we risk once they finally do? Definitely something to think about. Thanks so much for joining me today, and I'll catch you next time.